Hello, I'm Arno Kret. I work at the University of Amsterdam. My research is in arithmetic, so it's a field that lies on the intersection of algebraic geometry and number theory. So today I will introduce together with Bas Edixhoven the category of R modules. So before going to the precise definitions, let me give a brief motivation for why you would like to study R modules. So maybe you have seen when you follow the course on group theory that for groups it is very important and very useful to look at G-sets. Even if you're only interested in properties about groups, it is very useful to make groups act on sets. So with rings we try to do the same thing. So to study rings, it turns out to be very useful to make rings act on other objects. And for rings it turns out that the natural thing to do is to make them act on abelian groups. So this leads you to the definition of R modules. So I'll write down the definition now. You'll see that actually it's very similar to the notion of a K vector space, but now we just relax the condition that K is a field to the condition that K is a ring. Okay, so let me write down the definition. So definition, let R be a ring. So associative and has a unit element, but we don't require that it is commutative, so maybe even be a non-commutative ring. So let R be a ring. Then an R module is a triple consisting of three things: a set, a map, and another map. So M is a set, like I said. The plus is the map is a map from M cross M to itself. The addition, and I also have a scalar multiplication, which I'll denote by a dot, which goes from R cross M to M. So this is called scalar multiplication, such that the following axioms hold. So I first ask that the pair n comma plus is an abelian group. So this addition really satisfies the axioms of a group. And then for all R prime and R, and all M and M primed in M, we have basically the usual rules of arithmetic. So if I take an element in my module and I multiply it with the sum of scalars, then I can expand the brackets. Right, that's the distributive property. I could also multiply the sum of elements in my module with a scalar. So then I should also just expand like this. The third condition is if I multiply two elements in my ring, then of course I can let the product act on my element in the module, but I could also do it in two steps. I could first let R prime act on my element, get the result, and then let R act on it. Okay, so maybe I should have written here that these maps shall be denoted plus and R dot M, but as usual I often leave out the dot and just write R times M. Okay, so this is the definition.
I know we had a
Oh, and the one, sorry, so
There is an eraser,
Yeah.
if you want, on the left.
I've got so the last condition, this is not automatic, so I really have to include it. So if I take the unit element in my ring, then I multiply it with M, then I just get M for all elements in the module. Okay, so these are kind of natural conditions. We can deduce from them some further properties. So once you know these axioms, then if n plus n dot is an R module, and if I take some element in M and I multiply this element with the zero element of my ring, then what you can do is, you know that 0 is equal to 0 plus 0. So this is the same like this. And now I can use this distributive property R and subtract on both sides 0 of R times M to get that 0 of R times M is equal to the 0 element of M. Right? I carried out the subtraction in M, which is an abelian group, so element, whatever this element is, it has an inverse, so I can remove it, and I get that 0 of R times M is the 0 of M. So because of this condition, it is actually acceptable to remove this R from the index and just write 0. So to no longer distinguish between the 0 of M and the 0 of R in such an explicit way. Okay, so that's one basic property. And there's a second basic property, which you can prove by similar direct argument. Leave it as an exercise. So again, if I have a module over a ring, then I take -1 as an element of R, so a scalar, and multiply the element of my module with -1, then I get the inverse of my element in the abelian group. So you can check that this is really equal to the inverse of M. The idea is, of course, you just now write, instead of 0 equals 0 plus 0, you write 0 as 1 minus 1, and you expand, and you get the property. Okay, so to give some remarks. So I started by writing a module is a triple consisting of a set, a plus, and a dot. So we almost never write all those things, so we usually suppress that from the notation and only write M. But it's of course important to note that these plus and these dot, they are really important. They determine the structure of the module, right? So we often write simply m, where we should have maybe written m comma plus comma dot. Second remark, I'll also come back to this later. The above is what is called a left module. So you can also devise modules where you allow multiplication on the right. These are slightly different. I'll come back to that later. But in this course we will have the convention that whenever we say let M be an R module, then it is a left module, unless we really explicitly say we want to have a right module. Okay, so definition, some remarks. So now I'd like to give examples of modules. So the first thing to note, of course, is really that so examples. If R is K is a field, usually we denote fields by the letter K, then a triple M plus dot is an R module if and only if it is K vector space. Now this is just because the axioms that I wrote down are exactly the same. Okay, so for fields, this is not a generalization, it's exactly the same thing. Okay, so second class of examples are the standard modules. So if you have an integer n in Z, and I go back to our general ring, then we can take the set M consisting of all tuples x1 up to xn, or maybe I also allow 0, where xi is an R. So I take M, the set equal to this, and addition given by the component-wise operations. And addition plus coming from M cross M to M. Just given by if I have two tuples, x1 primed, xn primed, this goes to x1 plus x1 primed, xn plus xn primed. Okay, so you just add on all the coordinates. Similar for scalar multiplication. So R cross M goes to M simply by sending a pair of a scalar and a vector to the vector, where I just do the scalar product of all the coordinates. Or I should just say, here the product I take is just a product in R, right? Because R is a ring, so I can multiply. So this is the module. So we write r to the n for this thing. When we want to view r to the n as a module in this way. So if n is 1, then we just see that r is a module over itself. So if you want, that's another example. And the other one is if n is 0, and then you just get the 0 module. So it's the module, the unique module where the underlying set has one element, a unit element, and then there's only one way to make this into an R module. So these are, I guess, the most basic examples. Okay. So now I would like to discuss the right R modules. So I already mentioned it briefly, but let me write it out. So definitely, so right. So I'm hoping that you are able to guess what the definition is. So definition, a right R module is again a triple m plus m dot, where m and plus is an abelian group. As before, and dot is a scalar multiplication. It's a map. So now I like to write R on the right of M, going to M, such that the following holds. So such that for all n primed in M and all r primed in R, we have again the usual distributed property. M equals M R plus M R primed, and now M cross R primed. So if I multiply on the right with the product, it's the same multiplying in this way. And finally, again, if I multiply with the unit element, I just get out the module element itself. So again, as before, you can now deduce that multiplying with 0 gives 0, and that if you multiply on the right with -1, you get the inverse. Okay, so this is the definition of right modules. So let me mention, or let me try to clarify. So when I was learning these things, I didn't, for the first time, I didn't really understand what is the point of these right modules, right? Because the difference seems to be only notational. Instead of writing the scalars on the left, you now write them on the right. I mean, what's the point? Well, the point is that there is actually a difference, and that's in this third axiom. So what is the difference? So suppose I have n a left R module so then we saw that if you have two ring elements and you multiply on the left like this, what comes out is R primed Rn, and how it works with right multiplication. So if M is still right R module, I would multiply with this product on the right, then what you see is that it goes in the other way, right? So if I multiply here with the product, the axiom is saying this is the same as first multiplying with R prime and then with R, whereas in this case it's saying it's the same as first multiplying with R and then with R primed. So this is why these two notions are different. Another way to, so you can relate them. So when given a ring R, so definition, say R is a ring, I define R op to be the ring whose underlying set is just R, and I just take for the addition operation the usual addition from R, but I define a new multiplication just by doing the product of R, but then in the opposite way. So where the product of two elements in R op is just by definition the product in the usual ring, but with the order inverted. Okay, so then if I have defined the ring in this way, then a right R module is the same as a left R op module. Okay, so the notions are interchangeable, but you have to replace the ring by its opposite ring. So of course, if R is commutative, then R is R op. So there is no difference. So this is why when you did vector spaces, nobody ever talked about left and right vector spaces. It's just because it's the same thing. But since we allow non-commutative rings, there really are commutative rings that are not isomorphic to their opposite ring. So for those rings, the category of left modules can be very different, or there's no reason why it should look like the category of right modules. Okay, so the two concepts diverge for non-commutative rings. Okay, so this is what I wanted to say about right modules. I don't know how I am with the time.
Fine. We
Okay.
can record for 5 more minutes, more or less.
Okay, so then I can say something about a further comparison with linear algebra over vector spaces. So you saw that the definition was really similar to the definition of vector spaces. But I want to point out that if you work with R modules in general, this category behaves in quite a different way. And one of the first basic problems that you have to face when dealing with R modules is that there are many R modules that do not have a basis. Okay, so let me try to define what this means. So section most R modules are not free. Okay, with the word most, I mean most R modules that you will encounter in your coming 2 years in the master program will not be free modules. So let me define what is free. So let M be an R module, and let's say E of M be a subset. Then we say that E is a basis of this module if for every M in M there exist for every E in E a unique scalar let's call it RE in R such that RE is 0 for almost all E in E. So almost all means that this equality holds for all but finitely many elements of E. And my element M is equal to the sum E, E, RE times E in M. Right, so it's saying that any element of my module, I can write it in a unique way as a linear combination of my bases. So it's basically the same definition as for vector spaces. So for vector spaces, we know that they are all free, so that you can always find such a set. But for R modules, this is really false. Okay, so some examples. Take, for instance, R is equal to Z. And then I can take my module equal to Z modulo NZ. And then as soon as N is not 0 or plus or minus 1, well then this quotient is really a finite group. So, or maybe say it like this, if I had a basis, if I could write any element Z modulo NZ as a linear combination of something, well then I can just add n to it, and then I have a second way of writing it. So I see that such a basis cannot exist. Okay, so this is not free. Okay, so as soon as you have some torsion, the module is not free. So I had a second example.
We have 30 seconds left.
Okay. So a second example I leave as an exercise. Show that Q is not free as a Z module. Okay, so maybe based on the first example you think, okay, as soon as there is no torsion, then I know for sure it's free.
5 seconds.
But that's false for Q as well. So